Okay, so hi everyone again. Good to see you all. So thanks everyone for doing the midterm on Tuesday. It seems my first time setting exam, it seems I veered somewhat on the too long side, certainly given the circumstances of having doing stuff over Gradescape and at home and so on. But that's all going to be, the circumstances will be taken into account when you grades. The aim this semester is to make sure no one is disadvantaged by COVID and by the circumstances. So I wouldn't worry at all about your final grades, but to give you guys an opportunity to show your knowledge, show everything you know. If you felt you couldn't do that in within the time limit, then we are going to allow corrections to be submitted. There's two ways you can do this. One is that you can see the answers first and stuff, but then it's not really giving you the opportunity to show that you could have answered it if you had more time. So we're just going to treat this like a normal homework, basically, and that is due Sunday evening at 11 p.m. Okay, and you will get your final score will be an average. For questions that you submit a correction to, you definitely don't have to, but if you do, your final score will be average of initial and corrected scores. Okay, so I encourage you guys to do that, partly because it will get you a better grade, potentially, but also because there's a lot of value in spending some more time thinking about it and trying to figure out what you did wrong and so on. Hopefully the questions are designed to help you learn, even if they were a bit too many to do an hour and a half. So yeah, please do that. Okay, so last time, a week ago, before the midterm happened, we talked about how to do a circuit to implement a quantum Fourier transform, which cool was a Fourier transform on the amplitudes of a quantum state. So we had some quantum state that was like a superposition of different values of x, and we applied some unitary that does the quantum Fourier transform to it, and we turned it instead into a superposition with amplitudes given by the Fourier transformed amplitudes, capital AK. Okay, and then we talked about how you could use that to do quantum phase estimation. An algorithm where you basically work out the eigenvalue of some known unitary acting on some known eigenstate of that. Okay. And so today, we're going to be using all of that to do Shor's algorithm, which is, of course, an algorithm for factoring prime numbers. It's an algorithm that does it exponentially faster than the best known classical examples. So this is the most famous example of an exponential quantum speedup. Of course, it's not known that it's actually an exponential speedup over the best possible classical algorithm, but it is an exponential speedup over the best known classical algorithm. I want to emphasize that this is not in any sense the most useful example of an exponential quantum speedup that quantum computers can do exponentially fast. Does anyone know what the most useful example is? There's a single example that in practice will be basically entirely what quantum computers will be used for in the future. Most useful example of an exponential quantum speedup It's very simple. It's just simulating quantum mechanics. Okay. And obviously a quantum computer can simulate quantum mechanics efficiently because that's how it works. And obviously a classical computer can't, because otherwise there'd be no point having a quantum computer. You just simulate it on a classical computer. Okay. And simulating quantum mechanics is a hugely, hugely valuable thing to do. For chemistry, for material science, for anything else, you have some complicated quantum system. It's very, very hard to simulate classically and sort of work out what the dynamics are classically and the properties are, but on a quantum computer, you'd be able to use it efficiently. Factoring prime numbers is just the most famous example because it's the most, like interesting from a sort of theoretical computer science point of view. But it also, it's not purely some neat theoretical number theory thing. It also will have very significant practical importance. And so I want to start today. Basically, all of today is going to be classical number theory. All of the quantum mechanics was done last week. But I want to start today by very briefly talking about why being able to factor primes significantly would actually be significant. And this is, of course, because of the famous algorithm RSA, which lets you do so-called public key cryptography. Okay. So what does public key cryptography mean? Well, it means everyone. You have some public information that everyone has that lets you encode a message. This is the public key. But you make it so that it's very hard, very computationally hard to decode the message without the so-called private key, which is kept secret by one person. So the receiver has his private key. He shares his public key, his or her public key with the sender. And so the sender can encode the message, but only the receiver can decode it. This is, of course, very different from QKD. In this case, in QKD, the information was protected based on sort of information theoretic arguments, like they're just laws of physics of quantum mechanics, making it impossible to sort of copy that information and then decode it without Alice and Bob being able to detect it. In this case, what's protecting the information isn't some information theoretic thing that prevents them copying anything they want. It's just the computational complexity of decoding it. Okay. And RSA is a particular algorithm for doing public key cryptography. It's the most famous one. It works in the following way. So Alice, who's going to end up, actually I should make this Bob, because it's Bob who's going to receive the message. Let's stick with that convention. So Bob is going to start by choosing two large primes, P and Q. You might ask, how does he do that? right? How does he know that P and Q are prime and know that he's actually picking prime numbers and not just random numbers? Well, the answer is that actually he does just pick random numbers. And then it turns out that there's efficient algorithms to check if his random number k is actually prime. So these are called primality testing algorithms. Turns out this is an efficient sort of polynomial in the number of bits in k. And it's also a theorem, the prime number theorem, that the probability of k being prime is equal to roughly is roughly equal to 1 over log k. So all he does is repeat until k is prime. You have to do that sort of order log k number of times. That's fine. Okay. What we're trying to do is have this process be polynomial in the log of the size of your primes. Okay. It's also going to choose something else. It's going to choose some relatively small number called e. People often use for some reason, just convention, 65,337. But it just has to be some particular small integer such that the greatest common denominator of p minus 1 times q minus 1 and e is equal to 1. So e is co-prime to the product of p minus 1 and q minus 1. We'll see why this is significant in a minute. But the key point is that this, again, can be checked efficiently with the so-called Euclidean algorithm. So if necessary, we just keep trying random e's until we find one that's where this property is true. Okay. So we've picked. Jesus. Okay, I'll leave that. Okay, so she's picked these two numbers, p and q, and a third much smaller number, e. And finally, Bob is going to compute d such that d times e is equal to 1 mod p minus 1 times q minus 1. Okay, so because the greatest common denominator of p minus 1, q minus 1, and e was equal to 1, then there'll be some number d such that multiplying them together gives 1 mod p minus 1, q minus 1. And this can be found efficiently using the extended Euclidean algorithm. Basically the same thing as the Euclidean algorithm. You just keep track of a bit more. So Bob is able to easily compute d But now, he's going to reveal to Alice, but also to the rest of the world, the public key, which is just going to be N, which is the product of P and Q, and E. Okay, but he's not going to reveal P and Q separately. He's not going to reveal what D is, which is what he computed. Okay, now we need to see how the algorithm actually gets used to send messages. So the first step is to encrypt the message. Okay, so we're going to assume that Alice wants to send some message. And we're going to assume that she's encoded her message as an integer M that is between 0 and big N, the product of these two prime numbers. Okay, so they've worked out some code in advance of how, publicly, of how those integers little m relate to different messages, like, hi Bob, what's up, how you doing, why are we sending this secretly when we're not talking about anything. Maybe it gets encoded as the integer m equals 2,476,332, whatever it might be. Okay, and what she's going to do is she's going to send, not m, because she doesn't want anyone finding that out. She instead sends the number c, which is going to be m to the e mod big N. Okay. Okay, so yeah, so she sends m to the e, and if someone only knows E, N, and C, in principle, that uniquely determines M, but there is in fact no known polynomial time algorithm for finding M. Okay, even though the process she used, everything she used to encode M was public, and the encoded message C uniquely determines M, then there's no efficient algorithm for inverting her process. Okay. Now, Bob receives this message C, okay? And, you know, you might say, well, he's going to work out M, how's he going to do it? The answer is that Bob also knows what D is, okay? He computed D efficiently using his knowledge of P and Q, which everyone else doesn't know, they only know their product. And so he just does the following. He computes C to the power D, which is equal to M to the E times D, which is equal to, because we know E times D is equal to 1 mod P minus 1 Q minus 1, this is equal to M times M to some integer lambda times P minus 1 times Q minus 1. Okay. There is a theorem called Fermat's Little theorem that I'm not going to prove, but it is a very standard number theory theorem, and it's, if you think about modular arithmetic as group theory and you're familiar with group theory, then it's reasonably obvious. But yeah, I'm not going to prove it here. that says any number to the power p minus 1 is equal to 1 mod p for a prime p. Okay? So in particular, m to the lambda times q minus 1 all to the power of p minus 1 is equal to 1 mod p. But also m times lambda p minus 1 to the q minus 1 equal to 1 mod q. So the same number has to be 1 more than a multiple of p, and it has to be 1 more than a multiple of q. But those are both primes, so it also has to be one more than a multiple of p times q, so it has to be equal to 1 mod n. Hence, all of this is equal to 1 mod n, and we find c to the d is equal to 1 mod big N. Sorry, c to the d minus 1 is equal to 1 mod n, c to the d is equal to m mod n. Okay, and so Bob, using his knowledge of what little d is able to recover the message and work out what Alice was trying to send. So that is the entirety of RSA. We went over it pretty quickly, pretty high level, but hopefully it gives you some intuition for why, how public key cryptography works. This is the foundation of all modern cryptography. This and algorithms very similar to it. Anytime you buy something in Amazon or something like that, you're either doing RSA or elliptic curve cryptography or something that's sort of morally pretty similar to this. But it crucially relies on outsiders who don't have, only know big N and little e, not being able to find P and Q. Okay, so it relies on people not being able to factor numbers in any reasonably efficient time. Fortunately, the best known classical algorithm for factoring primes is something called the general number field sieve, and that takes a time that is exponential in, let's get this right, log n to the third log n to the 2/3. Okay, so it's not quite sort of order n, but it's certainly not polynomial in log n. It's certainly not polynomial in the number of bits of this product n. Okay, and so that is pretty inefficient. However, Shor's algorithm on a quantum computer takes a time, if it's done most efficiently, that is order log n squared times log n times log n. Okay, so this is polynomial in log n. It's roughly log n squared. It's much more efficient, exponentially more efficient. And so this would basically destroy RSA as a method of cryptography. You might say, well, isn't that a bad thing? RSA is like super useful and important part of the modern world. And the answer is that yes, it sort of is, but it creates really great market demand for quantum key distribution. Okay, so this is an example of what in the business world they like to call synergies. You have one group of quantum information people who work out how to break all current cryptography, and then that creates, you know, huge amount of money for the other group of quantum people who can then say, come use our quantum key distribution stuff. And hopefully by the filtering of research grants, that also ends up with money for the people who broke it in the first place. Also, of course, a lot of money if you can do Shor's algorithm before people think you can do Shor's algorithm, because then you can just know everything that's going on in the world. And either the NSA is paying you a lot of money, or you're stealing a lot of money from like everyone buying stuff off Amazon. So either way, you do make a lot of money. But yeah, fundamentally, you know, being able to do this on a quantum computer would absolutely change the world dramatically. It would not really make the world a better place. More than that, everyone, if it was public knowledge that people were able to do this, everyone would switch to other forms of cryptography, and it would just, you know, kill itself as a useful thing to be doing in any way. So, you know, again, the reason you build quantum computers is to simulate quantum mechanics, is not to do this. But that's all I'm going to say about RSA. Before we move on to Shor's algorithm, does anyone have any questions about that?
I have a quick question.
Yep.
Are you guaranteed that only one product of prime numbers will give you n?
Yeah, so P and Q are prime. So by the fundamental theorem of arithmetic, which if you guys have never proved, I recommend you spend some time trying to figure out how to do it, and then probably give up and look it up online. Right? This is you know, the uniqueness of prime factorizations of a number is something we all take for granted because it's drilled into our heads as little kids before we know how to ask questions, and it's actually surprisingly non-obvious, but it is true. Yeah, so n is equal to p times q, right? Because we made sure that p and q were primes, then that's a unique product. Shor's algorithm is just designed to give you some factor. It doesn't, Shor's algorithm won't tell you well, Shor's algorithm plus primality testing will tell you if the number n was really the product of two primes or not. But Shor's algorithm itself just tells you some number that is a factor of n. That clear?
Thanks.
I have a question about RSA. Is the issue that like the alternative classical methods for encryption are just much weaker than RSA, or that there aren't good ones?
The reason, so okay, there are other things that are used, elliptic curves and so on. Turns out they're vulnerable to Shor's algorithm too. I'm not going to talk about them, but they are. There are sort of post-quantum classical cryptographic algorithms that are built on things that we don't know how to do with a quantum computer. The reason people don't want to just like switch them immediately is that if you're trying to do cryptography, you really want to sort of the older and more standard the algorithm, the better, because, you know, people have been trying to break that for longer, right? If some like algorithm that's just come out in a paper last year and they claimed, oh, there's no fast classical algorithm to decrypt this is secure, we shouldn't really trust that, right? Like, yeah, no. Particularly because it's really hard to prove that things aren't actually possible. You know, none of these are actually, really, this isn't protected by some known fact about how hard it is to factorize primes. It's protected by the fact that for the last 100 years or whatever, or 50 years since computers, people have been trying to find efficient algorithms for factor primes, and they haven't found any.
Right.
And it's trusting that a criminal isn't smarter than research mathematicians and computer scientists.
Yeah.
Cool. Okay. So now let's move on to Shor's algorithm itself. And again, I want to emphasize that the sort of fun quantum part is really basically just going to be quantum phase estimation. We'll see in the end. Basically, all the new stuff I'm going to be introducing today is just going to be some classical number theory algorithm, which is not that exciting, but there you go. Okay, so the classical part of Shor's algorithm involves the following steps. Step 1 is that you pick a random number I'm going to call little a that is between 1 and big N. Okay. Step 2, we compute the greatest common denominator of a and n. Okay. Again, this is just Euclidean algorithm, very efficient. I'm not explaining the Euclidean algorithm, but if you haven't seen it, I recommend you looking that up because it's like possibly the most foundational algorithm in all of sort of number theory and stuff. It's also sort of roughly what you learned in school for how to like do long division, I guess. So in that sense, it's less interesting. Okay, so step 3 is that if this greatest common denominator of little a and big N is not equal to 1, then we've solved the problem, right? We just got very, very lucky, and you know, if big N is a multiple of P and Q, then the greatest common denominator would have to be either P or Q, and we just got really lucky and we worked it out. But in general, this would give us some non-trivial factor of N, which is all we want. In practice, assuming N doesn't have any small factors, which it won't if it's a product of two large primes, then this is very, very, very unlikely to happen, but it's worth checking anyway. Step 4, assuming that doesn't work, is we're going to use the quantum part of the algorithm. So this is sort of the interesting step to find the smallest R such that little a to the power R is equal to 1 mod N. Okay? So because we know the greatest common denominator is now 1, then there will exist some R for which this is true. But finding it is very, very hard in general. Step 5 is that if R is odd, we go, damn, that was a waste of time. Give up, return to step 1, and pick a new random number A. Okay. Turns out, yeah, finding R if R is odd is not useful. But you can show sort of with order 1 probability, we'll get something even. If R is even, then we can look at a to the power R over 2. Okay, that's again going to be an integer. If that is equal to minus 1 mod N, then again, we go, damn, that was a waste of time. Return to step 1. Okay, again, you can show that this doesn't happen too often. So if we try a few times, then it'll all work out. Finally, if neither of those two things are true, then we have a to the R over 2 plus 1 times a to the R over 2 minus 1 is equal, obviously, difference of squares to a to the R minus 1, which is, of course, equal to 0 mod N. Okay? But, so the product of those two things divides N, but we checked in step 6 that a to the R over 2 is not equal to minus 1 mod N, So this means a to the r over 2 plus 1 does not divide n. And also a to the r over 2 minus 1 can't divide n, because then a to the r over 2 would be equal to 1 mod n, and by definition, r is meant to be the smallest number such that a to the r is equal to 1 mod n. Okay, so this also does not divide n, provided our quantum part of the algorithm works. It follows that the greatest common denominator, a to the r over 2 plus 1, and n, and the greatest common denominator, a to the r over 2 minus 1, and n, are non-trivial factors of n. Okay, if their product divides n, so say n is equal to p times q, then if their product divides n, if n divides their product even, yeah. Let me correct these. I didn't mean. So what I meant here was this is not divisible by n. It doesn't divide n. If the product of two numbers is divisible by n, but neither of the two numbers are, and n is equal to p times q, then one of them has to be divisible by p, and the other has to be divisible by q. Okay, and so by using our efficient algorithm for finding greatest common denominators, then we can find, we can find p and q from these things, and we're done. Okay. So the interesting part, the thing you can't just do on a classical computer, is this. This is where the magic of quantum computing and doing things in superposition and stuff is going to come into play. Okay.
I'm sorry, can you explain once more why a to the r over 2 plus 1 and a to the r over 2 minus 1 aren't divisible by n?
Yep. So by definition, little r is the smallest integer such that a to the r is equal to 1 mod n. Okay. And so that means a to the r over 2 is not equal to 1 mod n. Hence, a to the r over 2 minus 1 is not equal to 0 mod n. It's not divisible by n. Okay. We also checked in step 6 that a to the r over 2 is not equal to minus 1 mod n. If it was, we just gave up and tried again. And so that means that a to the r over 2 plus 1 is not divisible by n as well. Okay.
Great, thank you.
Awesome. Okay, any other questions about that sort of classical, how that classical algorithm works, assuming we can do this quantum part in step 4? Okay. Awesome. So now the interesting part of the proceedings going to be the quantum part of this algorithm. Okay, and there's a couple of ways you can think about this. Going to see in a bit that it's actually just secretly quantum phase estimation. But another way to think about what we're doing here is what's called quantum period finding. So what that means is we have some function f of x where f of x plus r is always equal to f of x. It's a function with periodic function with period r, and we want to find r. In this case, of course, f of x is equal to a to the x. Okay, but actually the algorithm will work for any function, periodic function like that can be implemented efficiently on the classical computer. Okay? So the key sort of unitary we're going to use is the following. Going to call it u a to the x. And we're going to define this to map x tensor with y, where y is going to have n equals the ceiling log base 2 of n, big N qubits, okay? So y is going to be big enough to store numbers up to big N, and x is going to have q qubits for q that I'll define in a minute. And our unitary is going to map this to x, y plus a to the x mod n. Okay. So this is just the usual thing of we're taking some classical function and we're applying it to the y qubits based on the x qubits. And the key point is that a to the x is efficiently computable classically even for large powers of x. So you might think, just doing a times a times a, the length of time to sort of multiply them all together is going to be order x, okay, which is very bad. If x is large, it's sort of exponential in the number of bits of x. But instead, we can use, it's called repeated squaring. What we do is we compute a squared, then a to the fourth, a squared squared, and then square that, mod n, and get a to the 8, and so on. Because this is just all mod n, and these numbers don't get larger and larger because they start getting bigger than n and just get smaller again because of how modular arithmetic works. Okay. And we just need to make that be bigger than sort of do that all the way up to sort of the number of bits of x, and then we just multiply a to the sort of 0 bit of x times a squared times the first bit of x, 1 bit of x. So x here is equal to, let's call it x little q. Yeah, so let's call this a to the 2 to the q, x little q minus 1, dot, 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 down to x0. That's the binary expansion of x. And then we just multiply a to the x0 times a squared to the x1 times a to the 4th times the xq2, so on, times eventually a to the 2 to the q times xq, okay? And that gives us a to the x, and the time required is order q, okay? Or possibly it's slightly more than q, but I'll just write order, it's polynomial in q. Much more efficient than just multiplying a times itself, times itself, times it, times itself, times itself. Okay, by quickly computing these powers of 2, a to the some power of 2, then we're then able to quickly compute a to the x for any power of x. Okay, So because this is efficiently computable on a classical computer, then hence, by the sort of general arguments we gave a few lectures ago, u of a to the x is efficiently computable. On a quantum computer. Okay. So u a to the x again is just this thing up here. We're just storing a to the x mod n in some second register, leaving x unchanged in the first register. Okay. So now we're going to do this, and we're going to choose q, turns out, such that n squared is going to be less than or equal to 2 to the q. It's going to be less than 2n squared. Okay, so q is going to be twice as large, basically, as little n, the number of bits we needed to store numbers mod n. Okay. So now we're going to do our algorithm. It's pretty simple. Going to start, as usual, with everything in the 0-bit state. So we have 2 qubits in the top register, q qubits in the top register, and little n qubits in the bottom register. Anyone want to guess what we're going to do to these q qubits in the top register? What do we always do? Where they're going to end up controlling this function f of x. And what's like the one trick we always start by doing? Any quantum algorithm? Someone?
Hadamard and everything.
Awesome. We're going to Hadamard all of them to turn it into a superposition over all possible values of x. Then we're going to apply this u a to the x, okay? And finally, it's very simple. We're just going to apply quantum Fourier transform. And then we're going to measure our q qubits. Okay, really a very simple algorithm. So let's just put a few times in here and look at how the state evolves. Quantum algorithms normally end up being not that complicated. I mean, the quantum Fourier transform is kind of complicated, and so that's all gone into one box. But just, they're very, very hard to come up with, so they don't normally have too many different steps compared to some classical algorithms, which are like completely insane and crazy. And yeah, you also wonder how people came up with them, but that's just because they're so complicated. Okay, so time t1, we've just taken our 0 states and we've Hadamarded the first q. Okay, so as usual, that's just going to give us a superposition over all values of x, and then the remaining qubits are still all just going to be in the 0 state, right? Okay, so now we're going to apply u of a to the x, and now, again, very simple. Going to have a superposition over x. And then here we're going to have a to the x mod big N. Okay. We can rewrite this in the following way just because it's convenient. As a superposition over u's of superposition over x's such that a to the x is equal to u of x times u. Okay, so u here is just a to the x, and we've just grouped together all the different values of x that have a to the x equal to u. Okay? And the key point is that if a to the y equals a, well, let me change my notation. A to the x prime equals a to the x equals u, then a to the x prime minus x is equal to 1. Hence, a x prime minus x has to be equal to some constant, which I'll call y, times r. Okay? Because by definition, a to the r is the smallest number, such that a to the r equals 1. And yeah, higher powers, after that, if I just take higher powers of a to the x, it's just going to cyclically go around in a cycle and come back to 1 every time we add r. Okay, so we can rewrite this as 2 to the minus q over 2 sum over all possible values of u, all the different values of a to the x, of sum over y x naught of u plus y times r tensor u. Okay, where x naught of u is the smallest x such that a to the x equals u. Okay. So we can even write this, actually let me rewrite this once more. It's equal to 2 to the minus q over 2 sum over x naught equals 0 to r minus 1 sum over y x naught plus y times r a to the x naught. Okay. Now finally, let's go to time t3. So all we're going to do now is we're going to apply quantum Fourier transform to this state. Okay. So what do we get? We get an extra factor of 2 to the minus q over 2 at the front. 2 to the minus q. We get a sum over x naught and k. Sum over y e to 2 pi I k x naught plus y r over 2 to the q times k times a to the x naught. Okay. So we just Fourier transformed it. So we get this is just a coefficient ak, where little a x was just 0 if x equals x naught plus not equal to x naught plus yr, and 1 if it is equal to x naught plus yr. In other words, the only terms in the sum are the sums over y. This sum is dominated sorry. Yeah, the sum is, yeah, I would say it's dominated by values of k okay, I really don't want to say it's dominated. This sum is very small. Let's try that. Unless k r over 2 to the q roughly equal to some integer, which I can call m. Okay, so this is just a sum. Ignore the e to the 2 pi I k x naught, because that's the same for all terms of the sum. We can take it out the front. This is just a sum over y of e to the 2 pi I k y r over 2 to the q. Okay. If kr over 2 to the q is roughly equal to an integer, then all these terms in the sum are going to have a phase very close to 1. Okay? And so they're all going to add up in phase, and we're going to get something significantly bigger that can potentially cancel out a large part of this very small number 2 to the minus q at the beginning. If it's not very close to an integer, then these phases will be cycling around a circle. They'll all cancel out, and you'll get something much, much, much smaller. It's just exactly the same thing we found last time with the quantum phase estimation. I'm not going to go into detail justifying sort of the error bounds of how close it's going to be, but all we're going to do is we're going to take that answer for k, and measure k, and then we're going to use the so-called continued fraction expansion again. If you haven't seen this before, definitely look it up, but it's sort of tangential to the discussion, so I don't want to talk about it in detail, of k over 2 to the q to find candidate values for the fraction m over r. Right, we expect k times r over 2 to the q is very close to some integer n. So that must mean that k over 2 to the q should be roughly equal to m over r. So we just find explicit fractions m over r that are very close to k over 2 to the q. Okay? And then we just find such fractions, and then we check classically whether a to the r is equal to 1. Okay. If it is, then we're done. We maybe need to check that a to the r over 2 is not equal to 1 or anything. But as long as we took the fraction, we canceled out factors between little m and r, then it should be the smallest r. And so if this is true, then we're done. We can plug this into a classical part of the algorithm and end up factorizing our primes. If no, then we try other candidate fractions. We look for other things in the continued value expansion that are, gives very good approximations for k over 2 to the q. If none of them work, we just go, okay, we'll just try the whole quantum algorithm again.
So does this imply there's no guarantee that you can get one given?
Yeah. So it's an algorithm for BQP, not EQP, right? It only has to succeed with high probability. So that was a comment I was going to make here. That there are lots of failure points in both the classical and quantum algorithms where we just sort of give up and try again. Okay? But can show, I didn't really do this at all, but it can be done, and hopefully at least the quantum part should be intuitively obvious that this is true, given our discussion last time about quantum phase estimation. Can show that the sort of probability of succeeding is some order 1 number. It's independent of big N. So if we run the algorithm, some large but order 1 number of times, then we can get the probability of succeeding and finding factor to be very close to 1. Okay. The other comment I want to make is about the runtime of this algorithm. So if we assume that the limiting factor is our quantum computer, because probably our quantum computers aren't as good as our classical computers, everything classical computers doing pretty easy, then there's really 2 steps here, right? You've got the quantum Fourier transform, and you've got applying u of a to the x. The quantum Fourier transform we found last time takes order little q squared gates to apply. U of a to the x, it turns out, is slightly harder than that. So slowest step is applying u of a to the x. The sort of naive algorithm that I described above where we're doing these squarings. Each squaring done very naively takes order little n squared time. We have q of them, and then we've got to multiply them together. Whole thing ends up taking order little n cubed time. Best known algorithms, sort of best known classical algorithms for doing evaluating a to the x mod n. Actually let you improve that somewhat. To order n squared times log n times log n. Okay, and recall that little n is like log of big N. So this is log big N squared, log big N, log big N. Which is indeed what I claimed at the very beginning. And yeah, the key point is that it's polynomial in little n. Okay, it's roughly quadratic in little n, which is fast enough that yeah, it's comparable in the time to the time it takes to do the encoding in the first place. And in particular, trying to make the assumption that the NSA doesn't have the square of your computing power is not a safe assumption. assuming that they don't have an exponential amount of computing power to them compared to you is a very safe assumption, but assuming they don't have the square of your computing power is not a safe assumption. And in fact, I think the encoding time it takes more than linear in little n anyway. So I think they're really very comparable time to encode. If we have good quantum computers, then yeah, Shor's algorithm really will kill RSA as a form of cryptographic security. Okay, so the last thing I want to talk about is, at this point, it may not be obvious to you what on earth this has to do with quantum phase estimation. But we'll see it really is exactly the same algorithm. Just sort of viewed in a different way, written in terms of slightly different operators. We're going to define, instead of our unitary u(a) to the x, we're just going to define unitary that I'll call u tilde a. It takes in y on n qubits, and it outputs ay mod n. Okay, this is if y is sort of less than n, and let's just say it keeps y if y is greater than n. Okay, so this is a unitary because the greatest common denominator of a and n is equal to 1, then modular multiplication by a is invertible. So this is a well-defined unitary operator, and in particular, a previous operator that we call u(a) to the x, acting on x and 0, is exactly equal to x u tilde a to the power x acting on 1. Okay, so these are both equal to x a to the x. Okay, we've just written it in terms of this different operator, u tilde, instead of our previous operator that just computed a to the x and then stored it in this new register. Can read write Shor's algorithm in terms of u tilde of controlled u tilde a's as follows. We have our qubits that start in the 0 state. We had them on each of them. And we're going to start with our n qubits this time in state 1 rather than our state 0, because we're going to use this second thing rather than this first thing. So we want to apply u tilde a to the power x. How do we do that? Well, the smallest bit of x is going to be this bottom qubit. And so controlled on that, we're just going to apply a single u tilde here. Then controlled on the second one, we're going to apply u tilde squared. Finally, controlled on the largest bit of x, we're going to apply, I'm skipping out all the intermediate qubits, u tilde to the 2 to the q minus 1. Okay. So that's exactly the state outputted here by this inequality above is exactly the same state we had in a previous way of writing the algorithm, where we instead just plugged in 0 and plugged it into u to the a to the x. Okay, just rewritten it in terms of u tilde rather than u. So again, we just apply a quantum Fourier transform. And then measure all these output qubits. Okay. So this is just a way of rewriting essentially exactly the same algorithm. But it should be obvious that this is just quantum phase estimation for this operator u tilde, right? If you go back to the lecture last Thursday, you'll see that it is literally exactly the same algorithm I have written here. So why does this work? Why does quantum phase estimation solve this problem of finding R? Well, for any initial state Y, then it's easy to see that u tilde A to the power R is equal to A to the R Y mod N, which of course is just equal to Y, because A to the R equals 1 mod N. Okay? Hence u tilde to the power R is equal to 1. All eigenvalues of u tilde A are equal to E to 2 pi R I m over R for some integer m. Okay, they're all rth roots of the identity. Measuring k over 2 to the q gives us an approximation to m over R for some integer m. Okay, just because all the eigenstates are, the initial state 1 is not actually an eigenstate of u tilde, but because all the eigenstates of u tilde have eigenvalue e to the 2 pi I m over R for some value of m, then it's just a superposition over eigenstates with different values of m. And when we measure k at the end of the algorithm, it's going to give us one of those values of m. We don't have control over which one it is, but we get one of them. And then by finding fractions that approximate it, and using the fact that hopefully m doesn't divide R, and so they don't cancel out, then we can find R. Okay. So this is exactly what we found before when we were evaluating Shor's algorithm. It's the same thing we should expect if the algorithm is doing a good job at quantum phase estimation. It really is just an algorithm for quantum phase estimation. Okay. I think that is basically all. Anyone have any questions?
This is a simple question, but a while ago when we were doing the steps of the classical part of Shor's algorithm, what were the bounds on A? It's
just between 1 and big N, just a random number between 1 and big N.
I see. And then big N is the PQ, and then little n is just the number of bits. And
exactly. Yep, little n is
or
the
is it
number of
number-
bits in big N, and little q is just 2 times little n, roughly. Yeah, I should maybe have that explicitly written. So it's slightly confusing to have both q. So q roughly equal to up to plus or minus 1, whatever, is going to be 2 times little n.
I see.
So yeah, the reason, by the way, I didn't really emphasize the reason for choosing that size for q. So it's important for this step where we assume that these sums over y is dominated by the things where kr over q to q is very close to an integer, that we need to have q be big enough. And the reason for that is that we need the number of terms in the sum to be large. Right, if I only have 3 terms in the sum, it doesn't really matter if they all have the same phase or not. It's only if I have some very large number of terms that it really gets dominated by stuff where the phases all agree. You can check x naught has to be between 1 and n, right? Like yeah, like r has to be between 1 and n. So if we make the number of terms in the sum, we make sort of little x go up to n squared, then that ensures that there are at least order n terms in each sum, and that is enough to ensure that the enhancement for each of the things where they add up in phase dominates over just the fact that you have n different possible outcomes, n squared different possible outcomes. Okay. But yeah, don't worry too much about the details of the scaling. The important point is that as long as we've made little q big enough, then we have a really large number of terms in this sum, and if it's not, if they're not adding up in phase, then they're just gonna be really suppressed, and yeah, they're not gonna be significant.
I see. And up until the point that we measure k, r is just some arbitrary number that we don't know. We're just positing that it has the properties that we want.
Exactly. We know there's some r, but we don't know what it is.
I see.
Yeah. Any other questions? I want to emphasize that there was a lot of like number theory sort of stuff in here. This lecture is a bit of an odd one out because it just so happens that the most famous result in all of quantum computing is mostly about classical number theory, and then using that to take the one thing, one of the 2 or 3 algorithms quantum computers are good for, and use it to do something famous. Classical famous thing. Yeah, you do not need to remember all the details of this lecture. It's not really going to show up too much in homeworks. It's certainly not going to show up in the midterm or anything like that. But the thing you should take away is that really the key magical thing that quantum computers let you do is do quantum phase estimation, do quantum Fourier transform, and hence quantum phase estimation very efficiently, and that with some yeah, let's do too long didn't read this lecture. Prime factoring. Hardness of prime factoring. Protects RSA, and hence your shopping from being stolen. your credit card details from being stolen and so on. Using some classical tricks, so point 2, using some classical tricks. Prime factoring ends up being equivalent to finding little r such that a to the r, finding smallest little r, a to the r equals 1 mod n. And finally, quantum phase estimation / quantum period finding it's really the same thing. Lets you find little r. Okay. Any other questions? Yeah, if you take away those 3 points from this lecture, that is what all I would say is worth taking away. I would instead spend the time thinking more about how quantum phase estimation works and how the quantum Fourier transform works. Not that we'll need either of them terribly much more in the course, but they're at least like interesting quantum mechanical effects and not just some classical number theory that happens to be relevant. Okay. Any more questions? Okay, awesome. I think we will leave that there. Midterm corrections due on Sunday.